Hello and welcome back to Math Tutorials. Today we're going to be talking about antiderivatives, also known as indefinite integrals. Um, so what is an antiderivative? Well, it's pretty much just as the name suggests, the opposite of a derivative, right? Let's say we had something like x squared, right? If you differentiate that, that goes to 2x, right? Now antiderivatives would say, oh, if I take this, right? What's the antiderivative of this? Well, that would go the other direction. So the antiderivative of 2x is x squared. Um, but you also have to add something, right? Because let's say, so let's do this. So the derivative of x squared is 2x, but the derivative of x squared plus 3 is also 2x. So really, if I just give you 2x and say, what function did I find the derivative of to get this 2x, right? There's really an infinite number of possibilities. It could be x squared, it could be x squared plus 3, x squared plus 4, really x squared plus any constant. So really when we do anti-differentiation, we like to add a plus c, 2x, or x squared plus c. And this c stands for just any constant, right? Because really there's no way of finding out, right? So again, this is pretty much the opposite of differentiation. I like to think of it as a staircase, right? Where you have a function, right? Let's say you have a function here. You want to go down the staircase by differentiating. You can go down the staircase again by finding the second derivative, or you can go up by doing the antiderivative, which kind of has, this sort of, not that, this sort of symbol, right? The integral sign, because really it's an indefinite integral, right? An integral would be like, you know, I'll probably cover this next video, but it's like, from A to B, right? F of x dx, but this is just, basically this, but no a or b. So it's kind of just like a general formula. And then you would plug in the a and b into it and subtract. But anyway, this is kind of how I think about it. So let's say you want to find the first derivative of f. That'd be the same as finding the second derivative of the antiderivative of f, right? Because you're going down 2 steps versus starting here and going down 1 step, you're in the same place. So a common application for this kind of idea is that of physics, where you have, right, you could say like this is, you have like acceleration, and then you have velocity, and you have position, right? And you're kind of like going up this staircase every single time, right? If you do derivative, change in position is velocity, change in velocity is acceleration, and of course, antiderivative of these things, you just go back up the other way, right? So let's do a practice problem. I have one pulled up here. So find antiderivative. Yeah, perfect. All right, of this 3 over x minus 2 over x squared. So the first thing that I would do is write these not in terms of denominators, but in terms of negative exponents. So I would say 3x to the negative 1, right? Minus 2x to the negative 2, because recall this is the same as this. Well, same as that being the denominator. And now we can do a kind of reverse power rule. So if you think about the power rule, right, like I had earlier, x squared goes to 2x, right? Let's say like, x to the third goes to 3x squared, right? So what can we do here? Well, let's see. It seems like we're going to, if this is decreasing the exponent by 1, we're going to increase it by 1. So if we increase it by 1, that becomes 3x to the 0. And that would just be 3, there's 3. It's kind of weird. And that basically, we're going to see that doesn't really make sense. So we're going to keep that. We're not going to do it for this one. But for this term, we can do it, right? So that would be 2x to the, you add 1, so negative 1, right? And this is supposed to be negative. And now we check. If we take the derivative of this, do we get this? Let's see. The derivative of this would be what? Multiply by negative 1, so that'd be negative 2. and then x to the negative 2. So it looks like we get it, but we don't, because look, we multiply by negative 1, right? Here we have a negative, and then actually there'd be a negative out here too. So in reality, this is actually not the same as this. So we need to make one small change to our antiderivative, which is we need to multiply by negative 1, which basically just means, you could do the times, like this, but really that just means making this a plus sign. Now what about 3 over x? Now this is actually something special. Now basically if you have the antiderivative of 1 over x, I'm not going to go through a whole proof here, mostly because I don't remember it, but basically you can show that equals the natural log of x plus c, of course, because always plus c. You're going to miss a lot of points on your test if you forget the plus c. But basically, what we have is if you have something in this form where you have a denominator with some function, and then the numerator is the derivative of that function um, in terms of, whatever variable you're doing. And so you see here that we have the denominator is x. What's the derivative of x? Well, that's just 1, and the numerator is 1. Oh, and this equals the natural log of u. So we put basically the denominator into the natural log because the numerator is the derivative of the denominator. So here, right, we have this. Is the numerator the derivative of the denominator? Well, the denominator is x. The derivative of x is 1. So unfortunately, this is not the derivative. But what we can do is we can kind of factor out the 3. We could say, really, we actually just have this, right? And because this is multiplying by a constant, what we can do is, move this to outside of the antiderivative, right? And then we can say, oh, well, that's just 3 times, right, this part, ln x. And I'm not going to put the plus c because you can put that at the end. So basically what we have is here, right, our full antiderivative, let me write this out again, 3x to negative 1 minus 2x negative 2. The antiderivative of this, I'm bad at drawing these things. I think everybody's bad at drawing these things, though, to be fair. The antiderivative equals, or the indefinite integral, same thing, is 3 ln natural log, right? I just like saying ln for whatever reason, plus 2x negative 1 plus c. And then, of course, you can write this as 2 over x, right? So that's the process for that. And now, of course, there's a bunch of, that's the process for this one right here, this problem. Now, there's a lot of different methods for doing anti-differentiation. Unfortunately, a lot of them end up being, I would say, harder than their derivative counterparts, because you kind of have to think about it as, a puzzle where you're given the answer and you're trying to figure out what the question is, which I think is a lot harder. Another one we can look at is chain rule. So if I had something like, f of x equals, sine of x squared, right? The derivative of that would be, well, let's see, derivative of the inside, right? So 2x, oh, and then derivative of sine is cosine, so that'd be 2x cosine x squared, right? Because it's, right, if you have f of g of x, right, the derivative is derivative of g times derivative of f of g of x. I believe that's right. Let me just make sure. Yeah, okay. So now what if I was given, right, let's say I was given, well, to use the exact same example, if I was given this, right, what would I think? So if I was given this and said, find the antiderivative of it, right, I would say, okay, well, we know that it seems like it's going to be a chain rule type thing, right? Because we have a power thing, we have an exponent there, we have a trigonometry thing there. So it's pretty safe to say that this looks like a chain rule type thing. Another way we can kind of think about that is you definitely have a function here, and then a function inside that function, right? So if this outside part is the derivative of the inside part, then we know we're looking at a chain rule, right? We know we're looking at something like this. And so the derivative of x squared is 2x. So in fact, we are dealing with a derivative and then the regular function here. So we can do is we can start matching these up. So we can say this part is the g prime. We can say this part is the g, and then we can say this part is f prime. And so what we want, right, is f of g of x. Now what you notice is we already have the g of x. We already have half of our thing basically. So now we just need, so we know that g of x is x squared, right? So now we have to figure out what f of x is. But what we only have the derivative of x or of f. So basically we're looking at this part, this cosine part, and we're trying to think what's the antiderivative of cosine. And if we remember our little like cycle here, right? Sine, cosine, negative cosine. Remember, derivatives go like this, right? Which means antiderivatives go the other direction. So from cosine, which is what we have, it would be sine. So we know that f is sine x. So f of g is sine x squared. So that's how, and then, of course, kind of stupid example because we already knew, right? But, that's how it is sometimes. Let's see, what are we at? 11 minutes? Yeah. I think that's a pretty good example. Because of course this is supposed to kind of just be a quick thing. I think honestly, for the most part, you are just gonna see like chain rule stuff. There was a lot of chain rule stuff last year, and a lot of like power rule stuff. Well, reverse power rule, I guess. I don't actually know that's what it's called, but I would say this right here is an important concept, right? Identifying which parts are which, because you're gonna have, if it's chain rule, you're gonna have G prime, you're gonna have F prime, and you're gonna have G. So you have to match up which two are the derivative and antiderivative pair, right? Which in this case it's these two, which means you already know that this one is going to be part of your actual thing, right? It's going to be the inside function. So if it's chain rule, you should already know the inside function, and then it's just a matter of finding antiderivative on the outer function, right? This cosine turns into that sine. And then of course, I would say power rule is pretty easy. And of course, this video is kind of just supposed to remind you. If you never knew how to do this in the first place, this video was definitely not sufficient to teach you. But hopefully, this is a good reminder of kind of what to look for when you're doing antiderivatives. And remember, these are going to be harder than their derivative counterparts for sure. So definitely take the time to kind of remember how to do these. And if you have any questions with that, you can leave them in the comments. Tell me how I can make these videos better. Tell me how I can make them worse. Tell me what I'm doing good already, if I'm doing anything good. But yeah, okay. Let's see what we're going to do next week. I should probably do just like regular integrals, right? That would probably be smart. Um, yeah, yeah, I should probably do that. Yeah. So next time. Oh, that's big. Next time, definite integrals slash area. Yeah. Okay. Sounds good. Maybe even the Riemann two ends. Yeah. Sums. All right. So that'll be next time. But for now, thank you for watching. Goodbye.